my name is Covington, and my review today is going to be on Lesson 6, which was the atomic spectra and the Bohr model. The first thing to note is that anytime white light, for example the sunlight, goes through a glass prism, it creates a continuous spectrum of color, which looks like the rainbow. Here we can see all the colors from red, orange, yellow, green, blue, indigo, and violet. Sometime in 1814, a man by the name of Joseph von Fraunhofer noticed that the spectrum actually was not a continuous spectrum. In the spectrum, there was 574 dark lines that separated some of the colors. The lines can be described to look as a barcode. Within the spectrum, we are able to see separation of color now. It starts over here with red, orange, yellow, green, blue, indigo, and violet. And it increases in wavelength, starting from violet as the smallest to red as the largest wavelength. In 1859, a man by the name of Robert William Edbert Bunsen and his colleague Gustav Kirchhoff did an experiment to try to further understand the Fraunhofer lines. They heated elements and saw that each element could create a different color flame. With this, they noticed that every element had a unique sense of what color their flame would turn out. In other words, they discovered something called the emission spectra. As we can see, each element has a unique emission spectra. As we saw in the previous picture, each element has a unique emission spectra. In other words, for some atoms like helium, they would only emit light in certain places. And in the places that they emit light, it is a certain wavelength. So here, there's light being emitted at whatever wavelength this is. In the places that there is no light being emitted, for example, in all these other areas, that is where light is being absorbed. So only when light is at a certain wavelength or frequency, that is when light will be emitted. And in other elements, it can be emitted in more than one place as well. And for some elements, it's being emitted in a lot more places opposed to others. But likewise, with an emission spectra versus an absorption spectra, they're exact opposites. Anywhere light is being emitted is the exact opposite of where it's being absorbed. Visible light can only be seen when the wavelength ranges from 400 to 750 nanometers. There's a lot more places where light is being absorbed opposed to emitted. As we can see in each element, the absorption spectrum takes up a lot more space than this slight little emission spectra right here. As we can see in this picture, anywhere that the wavelength doesn't fall in between 400 and 750 nanometers, it falls into another category that would either be from the smallest gamma rays to X-rays, ultraviolet rays, the small portion of visible light, then infrared and radio waves. Radio waves have the biggest wavelength, but the smallest frequency. And since frequency correlates with energy, radio waves has the least amount of energy, and it just decreases going down the spectra. So gamma rays, which has the smallest wavelength, will have the biggest amount of energy and also the biggest frequency. We know because the equation E is equal to Planck's constant times the frequency, that frequency correlates directly to energy. Here we have a photo of a hydrogen spectrum with the emission and absorption spectrum. As we can see, they are exact opposites, or in other words, anywhere that light is being emitted, light cannot be being absorbed. Likewise, anywhere where the light is being absorbed, it cannot be being emitted. So what exactly does it mean when something is being emitted or absorbed, and what is being emitted or absorbed? Well, the thing that's being emitted or absorbed is a photon, or like a particle of energy or light. So according to the Bohr model, we have here a nucleus, and around the nucleus there are electrons going around in rings. The higher rings are more excited states, and here at the ring closest to the nucleus, it is the ground state. And when a photon is being absorbed, it goes from a lower energy state to a higher energy state. And then when it's being emitted, it's going from a more excited state back down. And it doesn't have to go all the way back to the ground state, but it goes lower to a lower state than what it was at. And that happens when photons are being released, and that comes off as emission, which is what helps us to see color. So as I've said, when a photon is being emitted or released, it's releasing the photons, which is helping us to see color if it's happening in the right wavelength, between 400 to 750 nanometers for the right element. And when it's switching between each energy level state, so for example, if it was going from 1 to 2, it makes a very large jump. But the more you increase in energy, the smaller this gap here in between each jump is. It gets lower and lower. And the energy level states are quantum numbers known as n. And if you go all the way up to n equals infinity, then you get 0. So since we know that photons are able to switch between energy levels, is there a way that we can tell where each photon came from? Well, this equation is known as the Balmer series and Rydberg equation. Basically, it's 1 over the wavelength is equal to Rydberg's constant, which is just 1 point some numbers times 10 to the 7th meters. Let me put my units. And so Rydberg's constant, and then in parentheses we have 1 over the final energy level squared minus 1 over the initial energy level squared. So if we have our wavelength, and we know that Rydberg's constant is just this number here, and we know either what our final or initial energy level state is, we need to have one or the other, then we are able to know where the photon switched from. And so basically, a way that you can tell if photons were being emitted or absorbed is what this center in between the parentheses turns out to be. So if it comes out positive, then we know that photons were being emitted and we're losing photons. So this makes sense because if we were to put it into the equation, so if we are going from the energy level of 5 and dropping down to 1 over 1 squared minus 1 over 5 squared is obviously going to come out to a positive number. Likewise, if we were to switch that and go from n equals 1 to n equals 5, then we would get a negative number. And so that means that we are absorbing photons and we're getting more photons. So let's take a look back at the Bohr model once again. Here we have our nucleus, and around it we have our different energy levels. So, as I mentioned earlier in this video, the lower energy level is known as the ground state. And at the ground state, that is where the electrons and photons are the most calm. There's the least amount of energy here. As a photon gains energy, it can go to a different energy level state. And also, as I mentioned earlier, there's something called quantum numbers, right? So here n is equal to 1. It's the first ground state. Here n is equal to 2. And with these quantum numbers, when photons switch in between states, it has to switch to a full number, or it can't be switching halfway in between one energy state to the other. It has to go completely. And the more energy of correlates to higher n's. So the bigger your n, the more energy you have. And the way that you gain energy is by switching from a lower energy state, so from the ground state to level 4, or from level 2 to level 4, or from level 2 to level 3. That's how you gain energy. Likewise, losing energy is going from an excited state to a lower state. So, is there a way to know what the energy in a specific orbital is? Well, in fact there is, and there's an equation known as the Bohr equation, and originally it was written as this really complicated equation with Z as the atomic number, and you'd have to know the electron's charge and the electron's mass, and this equation is basically the same as this equation right here. They're equivalent. So a simpler version is E equals negative H RH parentheses 1 over n squared. And basically H is Planck's constant, 6.26 times 10 to the negative 34th meters. And then RH is just equal to 1.0974 times 10 to the 7th meters. And so basically, you can know one of two things from this equation. If you know the E and you're solving for n, then you can solve for what the energy level that you're at is. And if you know n, then you can solve for E and know how much energy is in the certain state that you're in right now. The Bohr equation can also be used to find the change in energy. So here in the original equation we have E equals negative H RH parentheses 1 over n squared. However, we can take the same equation, and if we were to want to find the difference, we could take this right here, the first part of the equation, and just subtract it by itself again to find when the energy level was at its final to at its initial. But if you combine those two equations, it comes into a simplified version of the change in E is equal to negative HRH parentheses 1 over the final energy, or the final level squared, minus 1 over the initial level squared. And so from the Bohr equation, we can know either the energy level of a certain state or the change in an energy level from one state to another. So when our answer in the Bohr equation gets a positive energy change, what does that mean? Well, that simply means that energy was being absorbed. So we started here at a lower energy state and we absorbed photons, and now we're in a higher state. And this makes sense because if we were to look at this equation and we're starting from n is equal to 1 and we're jumping up to n is equal to 5, then we're going to get a negative number inside our parentheses. But since the Bohr equation has a negative in front of the HRH, it'll a negative times a negative is equal to a positive. So anytime we have a positive change, we're adding photons, then that's what that means when the energy change is positive, is when we're going from a lower energy to a higher energy. And when we're going from a lower to higher energy, that means that we are absorbing. So let's look at the exact opposite case. When the change in energy is a negative change, then that means we are emitting photons. So we are going from a higher energy state down to a lower energy state. And these photons are being emitted. And as we mentioned earlier in the video, anytime it's being emitted at the right wavelength, then we have a possibility to see color. And so let's look back at this equation. So if we were to start at n equals 5 and go down to n equals 1, then we are going to get a positive number here, because 1 over this 1 squared minus 1 over 5 squared, we end in a positive number. And here the constant is negative. So a negative times a positive is equal to a negative. And so basically, anytime we see our change here, if it comes out negative, we know that we're emitting. If the change comes out positive, we know that we are absorbing photons. Something that I wanted to point out was that, or has to do with when we see color. So we know that when we are emitting or giving off photons, we are losing them. And if it's being lost at the right wavelength, then we are able to see this in color. However, we can also see color in another way, and it does happen when photons are being absorbed. So sometimes when photons are being absorbed, everything is being absorbed at a certain wavelength except for one color. So for example, if I were to see the color green, that could also mean that the thing that I'm seeing green at is just reflecting off that color. So all the other colors in the rainbow is being absorbed, but the color green is being reflected off of that thing. Really quickly, I just wanted to cover what the relationship is between these three equations. So here we have the change in E, and we saw earlier that we can also solve that from a different equation, but that's also equivalent to Planck's constant times frequency. And we know that frequency, so if we are ever given a problem and we are given wavelength and asked to find the change in E, then that is still possible, because we know the correlation between these three equations. So wavelength or frequency is equal to Planck's constant times c, which is the speed of light, over a wavelength. And if we're given the wavelength, we can calculate our frequency, plug it into this equation, multiply that by Planck's constant, and then get the change in energy. So that's the end of the lesson. Let's do some practice problems to check our comprehension. So the first question is, which has the greatest change in energy? So here we have going from n equals 1 to n equals 5, n equals 2 to n equals 5, n equals 3 to n equals 4, n equals 4 to 9, or n equals 2 to n equals 6. So for this question, we can plug it into the equation to find the change in energy is equal to those constants with 1 over the n final squared minus the 1 over n initial squared. Or we can kind of use our common sense for this. And we know from earlier that when we have the atom and the nucleus, it takes more energy to go from a lower state to a higher one. And so the lowest state here is 1, and we're making a pretty big jump to 5. And that jump is bigger than the rest of these. Going from 4 to 9 or 2 to 6 can also be big jumps, but not as big as 1 to 5, because the biggest gap is going from 1 to 2, and that has the biggest gap right there. Now, is this all these transitions emission or absorption? Well, we're going from a lower energy state to a higher one in each of these examples. So that's how we know that we are absorbing, because we are getting more photons, and when we get more photons, we go from a lower energy state to a higher, more excited one. And the more photons you have, the greater amount of energy that you have. So now let's see if we can solve the change in energy if we are going from n equals 3 to n equals 4. So first, here we have our equation. The change in energy is equal to negative HCRH times 1 over NF squared minus 1 over N initial squared. So basically all we have to do is plug in our numbers to this equation. So H is Planck's constant, which is negative 6.626 times 10 to the negative 34. C is 3 times 10 to the 8, which is the speed of light. And R is 1.0974 times 10 to the 7th meters. Okay, have our units here. And then we are going from n equals 3 to n equals 4. So we have our final squared over our initial squared. So all we have to do is get a calculator and plug everything into this equation. So what I like to do first is do this inside parentheses. So it comes out to negative. So first let's check. So I get negative 0.0486. Now, does this make sense? We have a negative number in here, and it does make sense because we are going from a lower to a higher energy level state, which means that the change should become positive, and a negative times a negative is positive. So now we just multiply that by each of our constants. So the final answer that we get is 1.06 times 10 to the negative 19th, and that is the change in energy, so that would, our units would be joules. So now we're going to ask for something different but a part of the same equation. So since we have, if we're given our change in energy and we're given our final state and we're asked to find what state we came from, we can also find this answer. So if we're given the equation, the change in energy is equal to negative HCRH with the parentheses 1 over NF squared minus 1 over the initial squared, then we can solve for x squared here because we have our change in energy, we have our constants, and we also have our final state. And so obviously these numbers that I made up were just made up, but as long as you understand the concept of where each part falls into the equation, then you can solve for what the initial energy state level came from. But once again, my numbers are made up, so when asked this for a real element, the numbers will come out right. So the final problem that we're going to work here is one that we were given in class when we were asked to find the change in states when we're given the wavelength. So in class, the wavelength that we were given was 434 nanometers. The first thing you want to do is change that immediately to meters because in order to work with it in the equation, we need it to be in meters. So the equation here that we have is 1 over the wavelength is equal to RH in parentheses 1 over NF squared minus 1 over NI squared. So we know what our wavelength is, and we know this is a constant number, so we are just going to plug it in and get that our answer should be equivalent to about 0.2099. So in the problem, it said that we're going from a high energy state to a lower energy state. So we want our Ni to be higher than our NF. So here I'm started with an initial of 5 and dropped down to 1. When I plugged it in, it came out to 0.96, and that is much bigger than 0.2099. So I knew that I had to go to a smaller amount. So I tried switching from the energy level of 4 to the energy level of 1, and I got that that was still too big. So I tried switching from n equals 4 to n equals 2, and that number came out close, but it was too small. So then I switched it to go from the energy level of 5 to the energy level of 2, and that energy level was correct, and I got the answer to be 0.21, which is exactly close to 0.2099 if we round to the nearest hundredths place. So that is how we can solve for the energy levels when given the wavelength. So that was the end of the review on Lecture 6, the atomic spectra and the Bohr model. Thank you for watching. I hope that helped.